Hello everyone, welcome back to the channel. In this project, I will create a Python function that finds the inverse of a matrix from scratch. There is already a built-in function in Python that does this. However, just like my previous Python video, this project is to test our understanding of basic Python functions as well as the method of finding the inverse of a matrix. As you can tell by now, I will be using the Python programming language in this project. Before we begin our coding session, let's first revisit the meaning of inverse of a matrix. So it is said here that an n times n square matrix is said to be invertible or non-singular if there exists another square matrix B that satisfies the following equation. The matrix A, the first square matrix, multiplied with the matrix B is equal to the matrix B multiplied with A and is also equal to the identity matrix IN. And here in this equation, the matrix B is called the inverse of the matrix A. So another way we can interpret or write the previous equation is as follows, with A superscript -1, indicating that it is the inverse of the matrix A. So this is how we're going to find the inverse of a 2x2 matrix. 2x2 matrix means that the matrix has 2 rows and 2 columns. So suppose we have a matrix A and the values are A, B, C, D. So therefore to find the inverse of matrix A, we have to in the matrix we switch the positions for the values A and D and add negative signs in front of B and C, and this matrix is multiplied with this value that we calculate outside, which is 1 divided by the determinant of matrix A, AD minus BC. And we have to make sure that the determinant is not equals to 0, because if it is equal to 0, therefore the matrix A does not have an inverse, and it is known as a singular matrix. This is an example of finding the inverse for a 2x2 matrix. We have this matrix A with the following values. So therefore, to find its inverse, we multiply -1 with 5 and we get -5, and we minus with the product of 3 and -2, which is -6. And in the matrix, we switch the positions for -1 and 5, and then we add a negative sign in front of 3 and -2. So negative cancels it out, becomes positive, therefore we get 2. So -5 minus with -6, we get 1. So therefore the inverse for matrix A is 5, -3, 2, and -1. But what if we have a matrix that has more than 2 rows and 2 columns? For this, we are going to use what we call the elementary row operations, or also mostly known as the Gauss-Jordan elimination method. The first step is to write matrix A on the left and the identity matrix I on the right in that in that position, in that way at the end of that sentence right there. The next step, the second step, is that we reduce A to a reduced row echelon matrix. Whatever operations that we perform on matrix A are also performed on matrix IN, on the identity matrix. We reduce A, as mentioned in the second step, to a reduced row echelon matrix until we get an identity matrix A. So if A can be reduced to an identity matrix, then the final result of the operations shown on the right side is now known as the inverse for that matrix. In other words, the identity matrix that was originally put on the right side, if it the values that at the end of that row reduced row echelon matrix from A is now known as the inverse for that matrix. So if A can't be reduced, if A cannot be reduced to the identity to an identity matrix, this means that A is singular or non-invertible. To see this clearly, we have to look at an example right here. So suppose we have a matrix B with those following values, a 3 by 3 matrix. So we're going to find the inverse of this matrix using the Gauss-Jordan elimination method. So this is the first step. The matrix B that from the question earlier is written on the left side, and we separate it with this straight line, and on the right side is the identity matrix. We'll try to reduce the matrix B so that in the end it becomes an identity matrix. So if here first we're going to take the second row, and we're going to let's say in here we're going to subtract it with the first row that has been multiplied by 2, and this is the result of that first row operation. And so we continue with the next operation and the next one until at the end of this operation right here, as you can see, the matrix B has now become an identity matrix, and on the right side, what was originally the identity matrix now has different values in it, such as the values are 12, -2, 7, -5, 1, 3, 1, 0, and 1. So therefore, this is the inverse of matrix B. So this is the answer to our question. So I hope that to the process of finding the inverse of the matrix is understandable for now, because we are going to use this elementary row operation in our coding to find the inverse of this matrix. So I'm using Jupyter Notebook this time to perform the coding, and the instructions basically said that we're going to find the inverse of a square matrix of any size. In Python, there is already a built-in function that helps you find this inverse actually. That built-in function is located under the Python module called Numpy. So first let's see this built-in function. We're going to import Numpy, the Numpy module as np, and let's print out the inverse using this function np dot linear algebra dot inv. This is the function that the built-in function that finds the inverse. So let's use the matrix that we use, the matrix B that we use in that slide that I've shown earlier. So in the first row is 1, 2, and -1. The second row is 2, 5, 1, and the third row is -1, -2, and 2. As you can see here, this is the inverse for that matrix, and it is the same as what we find at the end of the elementary row operations that I've shown in that slide earlier. So as you can see, the Numpy module already has a built-in function to find the inverse of a matrix, and in this project we're going to find the inverse from scratch. So we'll try to avoid, we'll definitely avoid using this inverse function here. However, we can use other functions under the Numpy module as well. So those functions may include the ones that we're going to find the determinant of that matrix, and also to create identity matrices. So for the first line of our program, we're going to import numpy as np, and the first function, so our the inverse matrix function that we're going to create will be including some functions that some user created functions, meaning we're going to create some functions that will be applied in our main function to find the inverse. So that first function that we will be creating ourselves is called zero matrix. So this function will create a matrix with only the values of 0 inside it, with the size of rows and columns. We will provide the number of rows and columns here as the arguments for this function right here. We'll write a short statement to basically explain what this function does. And we're going to create an empty list to store the values of our matrix, which is 0 in this case. We'll be using the for loop to append those 0 values inside our A matrix here. The output for this function is obviously our matrix A. The second function that we will be creating here is called copy matrix, and it will take in one value, which is the matrix that we want to create copies of. First, we will find the number of rows, the matrix that we provide here, M. First, we'll find the number of rows this M matrix have, and we will be using this len function here. Same goes with finding the number of columns. We will find out the number of elements inside the first row of our M matrix. That is, so after we get the number of rows and columns, we will provide this as the arguments for our zero matrix function. And we'll store this in a variable called MC. Next, we're going to fill in the values inside this MC function here. So basically what they have right now is just a series of zeros inside MC here as elements of the matrix. So we're going to replace those zeros with values from the M matrix here. Again, we will use a for loop in the range of row and also in the range of columns. We'll fill this in each row. The output for this second function here is obviously the matrix MC. So now we can work on the main function, which is the inverse matrix function. It will take in the value of that matrix X, and let's add a short statement to explain what this what this function does. So basically it calculates the inverse of a square matrix. The function will check whether the matrix is inversible or not. If the matrix is inversible, then it will perform the Gauss-Jordan elimination method to find the inverse. if you can recall that the matrix is inversible if the matrix is a square matrix, meaning that the number of rows and columns have to be the same, and the determinant must not be equal to 0. So to check those two conditions, we will be using the if-else statement. So if the length of X here, which stands for the number of columns of the matrix X, is equal to the number of elements inside the first row of the matrix X here, basically which is the number of columns, we will run the rest of the program. But first, let me write what will happen if the number of rows and columns are not the same. Nothing much happens except we will be printing out some sort of like an error message saying that this is not a square matrix, therefore we cannot find its inverse. So basically, if the number of rows and the number of columns here are not the same, this message will be printed out. Otherwise, it will look at the second condition of finding the inverse of the matrix, which is to check to see whether the determinant is equal to 0. For this, we will use the function under a built-in function under the Numpy module called DET, determinant. So again, we will use this if statement here. So if the determinant is not equals to 0, we will proceed with our program. Otherwise, an error message will be printed out. Let's write this error message as the determinant is 0. Therefore, we cannot find its inverse, the determinant of this matrix. Okay, it's more clear. Okay, so these two conditions, which is whether the matrix is a square matrix and whether it is the determinant is not equals to 0. So if these two conditions are fulfilled, then we will proceed with the rest of the function to find the inverse of X here. So the first step to find the inverse before we perform the elementary row operations here is to create copies of the matrix X. So let's just simply call this a copy using the copy matrix function that we created. And we're going to create an identity matrix of the size similar to X here. So if X is, say, a 3 by 3 matrix, so we will have an identity matrix of the same size, 3 by 3. For this, we will use the identity function under the Numpy module, and it is in the size of, we provide the number of rows of X as our argument for this function, this identity function. And again, this identity matrix here will have a copy of matrix as well. When we perform the row operations, we will perform them on these A copy and I copy matrices that we create here. And first, let's create a variable called Indices. It's a list of the number of rows inside our X matrix here, and this is to ensure that when we perform the row operations, we will only perform it on a specific row, on just one row. We'll make sure that no similar operations can be performed on on a different row. We will work on, as you can see in the process shown in the slide earlier, the row operations are performed on each row, meaning that we work on only one row at a time until at the end of the process, we get the identity matrix and the inverse of that of the matrix. So for the rest of the lines of code here is basically just us trying to find the row operations. For a more detailed explanation on how the functions work, how the lines of code work, you can find out at the original source code that I referenced in the description box below. There is a detailed explanation there, detailed instructions, and this is just basically a simplified, for me it's I've simplified this version for better understanding of the row operations to find this inverse. So finally, we want to print out the results of our calculation here, and we'll print out the matrix that we provide here, the matrix X here. Let's say this as your matrix is, and using a for loop, we're going to display the matrix that we provide as X here in the matrix format. Otherwise, if we just simply print out the matrix, if we just use the usual print command here on our matrix X, it will come out in a list format in just one row, so it can be a bit confusing to some people. So we're going to use this for loop to print it in rows. And to print out the inverse of our matrix X here, we'll separate this with this straight line, this dashed line, and let's print out like a heading, a short heading here. The inverse of your matrix is, again, we'll use the for loop, and we're going to print out the inverse, which is the values of iCopy of the iCopy matrix. So now we can run these lines of code, and we can test this using the 3x3 matrix that we used in the slide earlier. Let's call that 3x3, sorry. Let's just simply, the name of our matrix here is inverse matrix, and this 3x3 matrix here will be our argument. And we'll run this. And as you can see, the first output is our matrix, our original matrix, 1, 2, negative 1, 2, 5, 1, negative 1, negative 2, and 2. And after this dash line here, we say that the inverse of the matrix is 12, negative 2, 7, negative 5, 1, negative 3, 1, 0, and 1, which is the same as when we use this inverse function from the Numpy module. So let's say that we try to remove one row from this matrix. See if we can get the error message that we created. So here it says here that this is not a square matrix, therefore we cannot find its inverse, obviously because we have 2 rows and 3 columns, so we cannot find the inverse. Then this error message is printed out. So basically this is the end of this project. If you have any questions or there are parts that you don't understand, feel free to drop them in the comment section below. If you enjoyed this video or you might have learned something new from this, please give this video a thumbs up and subscribe to my channel for more contents like this in the future. Thanks for watching!